All right. Hello, everyone. Thank you for tuning in to the Physical Geography 1. This is 252, the final review. So we're going to be reviewing the material for the final exam. The exam will cover labs 1 through 9. We did already cover labs 1 through 5 in the midterm review. So if you want to know more about labs 1 through 5, watch the midterm review video. It is linked, I think, in the description. It's linked in the description of this live stream link. And also, we're going to share that midterm link with y'all again in the announcements. We'll post it on Canvas. But the midterm is for labs 1 through 5, which will be on the final. And we are about to go over labs 6 through 9. Now, again, lab 10, which is the bonus, is not on the final. It's just 1 through 9. So we're going to start with lab 6. It's about atmospheric pressure. So you remember all the way back, lab 3, we talked about the atmosphere. And so now we're going to be talking about the pressure that's caused by the atmosphere. So we know that the atmosphere itself is held to the Earth's surface by gravity. Gravity is keeping all those gas molecules and everything to the Earth's surface so they don't float off into space. And the weight by gravity holding all those molecules to the Earth's surface is known as pressure. That's atmospheric pressure, is the weight from that gravity. And it's going to be strongest closest to the Earth's surface because gravity is strongest close to the Earth's surface. So pressure, you're going to feel it the most if you're on land. And then as you move up in elevation, like you get to the top of a mountain, the pressure is very thin there because gravity is not as strong. So the air is a little thinner, and so pressure is a little thinner. Now, there are 2 different factors that go into atmospheric pressure, and that's going to be density and temperature. So the temperature at which the gas molecules are at really affects the different kind of pressure, and then also the density of those gas molecules. So are they all tightly, densely packed, or are they spread out gas molecules? So density and temperature are very important, and they show the relationship with this formula. This is called the ideal gas law. And you don't have to solve any equations or anything with this formula. It's just showing you the relationship between pressure and density and temperature. So if one of them changes, the others are going to be affected. So if density increases, temperature increases. If temperature increases, density increases. So think of it like that. You know, if one of these variables changes, so will the other. And then for measuring pressure, we use an instrument called a barometer. It looks like this. Barometers are going to measure the air pressure, the atmospheric pressure, and they measured in units called millibars. So remember, pressure is measured in units called millibars. And then the average pressure that you're going to have at sea level, so like on the ground, is going to be 1,013.25 millibars. That's our average pressure at sea level. And then, of course, as you get up in elevation, it gets lower and lower. So we talked about measuring pressure, now mapping pressure. We map it with lines like this that are called isobars. So isobars, the definition, is a line that joins points of equal atmospheric pressure. So I want you to think of an isobar as each individual line. So look at this bottom line here. This bottom line represents 1,008 millibars of pressure. So anywhere on this one line, on only this one line, is going to be 1,008 millibars of pressure. So this point here is 1,008, this point here, there, anywhere that line touches is 1,008. So anywhere on that line is equal to 1,008. Now again, for another line, like maybe over there in Florida, there's that 1,004 isobar. Anywhere on that line, any point there, the pressure will be 1,004. So isobars just show you where the different pressure readings are. And then now that we know where the different readings are in the numbers, it shows us where the high and the low pressure is. So up at the top, up near Montana, is 1,024 millibars. That's our highest pressure on the map. And then all the way down in Florida is the lowest pressure at 1,000 millibars. So just showing you low pressure, where it's concentrated, high pressures up here. And then where our low and high pressure is really going to affect how the wind blows. So if you're in my class, I always say this, the wind blows from high to low. So wind goes high to low. And so the wind, how it's going to blow for this map particularly, it's going to start up there at that high pressure at the top near Montana, and it's going to blow downward across towards Florida. So the wind's blowing across the United States down towards Florida. So that's how the wind is going for this map. But remember, it's always going to blow from high to low pressure. And then we also talked about troughs and ridges. Troughs and ridges just show high and low pressure. If it's a ridge, ridges go up, so think high pressure. If it's a trough, troughs are low. And so anywhere that has low pressure is going to be a trough. So here, there's low pressure in the center, so all of these places are troughs. And then over here, there's high pressure in the center, so all of those are ridges. So remember, ridges go with high pressure, troughs are for low pressure. So again, I talked about how pressure is strongest closest to the Earth's surface, and as you go up in elevation, it weakens, it thins out. And again, that's because of the density and the gravity. So gravity is strongest closest to the Earth's surface. And so all these little red dots here represent our gas molecules and our atoms. And so they're very concentrated closest to the Earth's surface where gravity is strongest and holding tight to it. As you go up in altitude, gravity weakens and the gas molecules start to spread out. They're not as dense. So they lose that tight, packed, those molecules. They're very spread out. And so something to keep in mind is that if you go up 5.6 kilometers off the Earth's surface, so you're 5.6 kilometers from the Earth's surface, then 50% of the gas molecules, all that mass in the atmosphere is below you, and 50% is above you. So you're not halfway through the atmosphere, like distance-wise, but you are halfway through it mass-wise, like the concentration of the molecules. So that just shows you only 5.6 kilometers off the Earth's surface, half of the atmosphere is concentrated under you, and half of it's above you. So that's pretty much what you need to focus on for Lab 6 for the final. Focuses on these things that we talked about. This is what will be focused on the final. So that's Lab 6. Moving on to Lab 7, atmospheric moisture. So we just talked about pressure. So now we're going to talk about moisture and humidity. So there's key terms that are very important to this lab. Of course, atmospheric moisture, which is just the water vapor and the rain that's in the atmosphere. Any kind of moisture that's in the atmosphere is atmospheric moisture. And then we have our different key terms for humidity. So we know humidity is just the water vapor in the atmosphere, but there's different ways to measure that water vapor. So one of those ways is going to be absolute humidity. So it measures the density of water vapor. So again, density is how tight those gas molecules are packed in together. Are they all right next to each other, or are they spread out? Are they not dense? So absolute humidity is the density of water vapor molecules. Then we have specific humidity that measures the mass. So how many water vapor molecules, how heavy are they? So that's the mass of water vapor. Then we have relative humidity, which is what we see most common. This is what the Weather Channel gives you, is relative humidity shown as like a percentage. Like if they tell you it's 60% humidity, that's our relative humidity. And so that is the ratio between the water vapor and the air, the ratio between the water vapor and the temperature. So how much water vapor it is, also at what temperature it's at. So, the hotter it is, of course, the more humid it is, and it's sticky and muggy. So that's our relative humidity. That's what, again, the Weather Channel is telling you. And then our very last key term is dew point. So dew point is just the temperature at which air has absorbed the maximum amount of water vapor, and then condensation starts to occur. So when the air becomes saturated, which means it's full of water, and the relative humidity is at 100%. So when that percentage gets to 100, that is when the dew point is reached. So it's going to start, dew is going to start forming. That's why it's called the dew point. So those are all of our key terms. So something that you'll need to do for the exam is know how to use these different charts. So if you look in your lab manual, you'll have these two charts. One is for relative humidity and one is for the dew point. And we also talked about in Lab 7 a sling psychrometer. So that's the instrument where it has two thermometers and you wave it around, swing it around in a circle, and as you're swinging it around, the water on that wet bulb is evaporating. And so, your dry bulb and your wet bulb are going to have two different readings. And so then you use those readings with this chart. So dry bulb is just the regular air temperature. The dry bulb is reading whatever the temperature is in the room you're in, or if you're outside, that's your dry bulb, that's the air temperature. And then this number across the top, the depression of the wet bulb, all that is, think of it as the difference between the two thermometer readings. So whatever the dry bulb says and whatever the wet bulb says, you subtract them. So whatever the difference between them, and then you'll use your dry bulb temperature to find what the relative humidity would be. So let's say our temperature in the air, the dry bulb reading, is 40. Say it's 40 degrees. And let's say that the wet bulb is 32. So the difference there, subtracting them, is 8. So I'm going to look at 40 because that's my air temperature, that's the dry bulb. And then I need to find 8 and find where they meet together. So here's 40, 8's over there. And so they meet at 37. So for this scenario that I just described, the relative humidity would be 37%. So that's how you use this chart. You use the dry bulb reading, the temperature. You subtract it from the wet bulb, and then you use that to find what your percentage would be for the relative humidity. Now, it's the same thing for this chart for the dew point. It's the same thing for the dew point. You just use whatever the dry bulb reading is, that regular air temperature. You subtract it from the wet bulb, so you need the difference between the two, and then you use that to find where they meet in the middle. So let's say our temperature is 70, and the wet bulb is 66. So the difference there is 4. So I need to find 70, and then I need to find 4 and where they meet. So 70 meets with 4 at 64. So the dew point temperature is 64. So if it reaches 64 degrees, dew is going to start forming and condensation will occur. It'll probably start raining. So that is how you use these charts to find dew point and relative humidity. Remember, you just need the air temperature and then the difference between the wet bulb and that air temperature. Okay, so this is a part a lot of people I know struggled with or got confused about, so we're going to go through it again. It's adiabatic lapse rates. And so, this whole lab 7, talking about atmospheric moisture, we're talking about parcels of air. These big mass of air moving through the sky, moving up or down, and we want to know how the temperature in that parcel of air is changing. So the temperature in this mass of air, how is it changing as it goes up and down through the sky? And so if our parcel of air is dry, there's no moisture, it's dry, our rate at which it moves through the air is it's going to change 5.5 degrees for every 1,000 feet that it goes. So if it raises up 1,000 feet, it's going to change by 5.5. Now, if our parcel of air has moisture, let's say it's saturated, so it has all that moisture and condensation's occurring, you're going to use your wet adiabatic lapse rate. And that one is 3.2 degrees for every 1,000 feet that you go up. And a key thing here to remember is a lot of people were adding this to your temperature as you go up the mountain. A lot of people were adding it. So as you went up, they were adding the temperature, and the temperature is getting hotter and hotter as you go up a mountain. But think about it in real life. When you go up a mountain, it's cold. Like, there's snow on the top of this mountain, so it should be colder up there. Because remember, the pressure is thinner, air is thinner, it's just colder up there. As you go up through the troposphere, remember that main characteristic of the troposphere is that as you go up in altitude, temperature decreases. So remember, when you're using your rates and you go up, to subtract, always subtract. Now when you go back down, that's when you add because it's warmer closest to the Earth's surface. So we're going to do this together. So over here on our windward side of the mountain, we're starting with 70 degrees. So on the ground level, it's 70 degrees. And we need to first find what the temperature is going to be at our elevation A right here. And our elevation is 1,000 feet. So we're going from 0 to 1,000, which matches perfectly with our wet and our dry rates. It's 1,000 feet. Awesome. So are we going to use the wet rate or are we going to use the dry rate? So we're looking at this span of 1,000 feet right here. Are there any moisture? Is there any clouds? The answer is no. There's no clouds, there's no moisture right here. So in this span right here, we're going to use the dry rate because there's no moisture in this 1,000 feet that we're moving. So dry rate is 5.5, so we need to subtract 5.5. So 70 minus 5.5 is 64.5. So that is our temperature at this elevation of 1,000 feet. Now we need to go another 1,000 feet. So we're looking at this span from A to B and only this 1,000 feet right here. Is there any moisture, any clouds or anything in this 1,000 foot difference? Again, there's not. There's no clouds, there's no moisture, not according to our diagram, there's no clouds there. So again, we're going to use the dry rate again, and it's 5.5. So we subtract. So 5.5 minus 64.5 is 59 degrees. So now we are up here. We are at 2,000 feet in the air, and it's 59 degrees. And we need to go from B, now we're going up to C. So remember, we're only looking at this 1,000 feet in between B and C, and only that 1,000 feet. Nothing else matters. And once again, there's no clouds in between B to C. So once again, we're going to use the dry rate. And again, so we're going to subtract 5.5, and that gives us 53.5. So we have one more step to go. We're going from C to D. And remember, we're only looking at the 1,000 feet from C to D, so that in between 3,000 and 4,000. Do we see any moisture? Do we see clouds? Yes, we do. We see clouds and we see moisture. So now our air has moisture. It's going to be saturated. So now's the time to use that wet rate. So our wet rate is 3.2 degrees for every 1,000 feet. So we're going to subtract 3.2. Remember, subtract when you're going up. So minus 3.2 gives us 50.3. So that is our temperature on the top of the mountain, is 50.3 degrees. And so if you look back at it, it makes sense. 70 degrees on the ground level makes sense because it's warmer all the way down here than it's going to be up there. So 50 degrees, that's pretty cold. That makes sense to us. So now we have to come back down to the ground. We got to go all the way back down over here to E at ground level at 0 feet. And there's two ways you can do this. First thing to realize here is that on the leeward side of the mountain, it's always going to be drier. The air is so much drier. You're going to use the dry rate. So every time you're on the leeward side, use that dry rate because the mountain blocks the moisture from traveling over to that side. So use the dry rate when you're on the leeward side. So I'll remember, use that 5.5. And the only difference now is we're adding as we're going back down. So remember, we're going back down to the Earth's surface. It's getting warmer. All that heat from the Earth's surface, pressure is getting thicker. The air is getting thicker. It's just warming up. So we need to add 5.5. The thing is, we're going from 4,000 feet down to 0. So again, like I said, there's two ways to do this. You can either add 5.5 to your temperature 4 different times, or you can multiply your 5.5 times 4 and then add to that. Because remember, our rate is for every 1,000 feet, but we need to go 4,000 feet. So you can, like I said, add it 4 times, or you can just multiply 5.5 times 4 and add that. So what I like to do, instead of adding 5.5 4 different times as you go down, I just multiply. So 5.5 times 4 is 22 degrees. And so I add that to my temperature at the top of the mountain, and that gives me 72.3. So it's 50.3 degrees at the top of the mountain, and then back down on the ground, it's 72.3. When you do an exercise like this, you should always have a warmer temperature on the leeward side of the mountain than what you started with on the windward. Because over here, there's not moisture, so the air is drier and it's going to be hotter. Over here, there's moisture, so the moisture cools it down, and it's about 2 degrees cooler than it is over there, just from the moisture difference. So again, it starts off at 70 over here and ends with 72.3. When you do this on the exam, you want to make sure that you end with a higher number than what you started with. So those are our adiabatic lapse rates. Again, you will have to do this on the exam. So if you have any questions about this, please let us know. Reach out to your lab instructor. We're here to help. But yeah, so that's it for lab 7. So that's it for lab 6 and 7, what you need to focus on. And now Miles is going to come talk about lab 8.
So let's talk about the most important and crazy part of Alabama, severe weather. So let's talk about the air mass and the air mass characteristics. As we talked about in my class, these are the large, distinct air parcels that have uniform temperature, humidity, and stability. Those 3 concepts are important when we talk about the air masses because that's what's going to define it. These only form over land and seas in the high to low altitude. So if you think about the weather coming in off the shore of the ocean, it's that type of air mass characteristics that are easy to picture. So there's 5 types of air masses that we're going to talk about. There's the MP, which is the maritime polar, the MT, which is the maritime tropical, there's your warm moist air, your CT, which is your continental tropical, which is your hot, dry area, your CA, your continental Arctic, so like way up in Canada, very cold, very dry, and your continental polar, which is cold and dry, which is like, way up there too. Oh, sorry, that one's Canada. CA would be like Arctic Circle. Yes, Arctic in the name. So which type of air masses would be the most common in each of the following cities? So if you want to pause for a moment, think about that. We have done this in class, so if you need to flip back to your notes, you can try looking at it there. If you're watching this later and you're just watching the recording, pause it and try and guess. It's not too hard. For example, talk about Jacksonville, Alabama. We know where that is. And we're going to be all the way over here, which is maritime tropical, MT. So I'm going to let you guys do the other ones by yourself. So let's talk about the air fronts. So when 2 air masses collide, a buffer zone is created, and a narrow barrier between air masses then extends over several kilometers wide or miles wide. These fronts move in the direction of the strongest air mass and displace the weaker one. So they're going to come in and they're just overpowering that weaker one. So the one that is the more powerful is going to be the one it's going to be named after. And this is going to be depending on the heat, direction, and the moisture content. So it's important to keep in mind, is it very hot air or is it more cooler? Is it more moist? Is it going over it? Or is it just kind of meeting? So it's direction, it's heat, and the moisture content. So let's talk about the cold front. So here we have our cold air coming in and overpowering the warm air. So this is why it's called a cold front. So obviously it's displacing that warm air. It's going to result in heavy rain and rapid temperature drops. So when the temperature drops, the RH, you need to remember what that is. Think about it for a second. Relative humidity rises and then the dew point temperature is reached. So that's our cold front. So here we have our warm front. Our warm air is coming in, and our cold air is being displaced, as we can see in this lovely diagram. The warm air is going to be unstable and can result in slight showers, so it's probably going to rain. This creates shallow horizontal clouds, which you can see up in the sky when it's about to rain. This may be going to rain, but it's still warmer. This is what the clouds are going to look like. So we have our stationary front. So this is a very common one. And neither one is really replacing each other. As you can see here, it's meeting, but they're not really mixed, or they're not overpowered. There's a slight mixing, but neither one is truly shifting away. So then we have the occluded front. This one can be a little bit difficult. The occlusion is going to occur here. So we have our cold air and our warm air. Our cold air is lifting up that warm air. So the cold air is overtaking the warm front, but the difference here is that it cuts off the warm air from the surface from where the two fronts meet, and it's going to be lifting it up. That's important to remember, is how it's meeting it. So the direction is why the occluded front is different than the cold front. Okay, and now Mr. King is going to cover climographs.
Okay. Hello, students. We're going to talk about climographs. All right, so when we talk about climographs, we're talking about classifying climate. And we are doing a lot of this based off of vegetation, as you can see here. And how do we measure that? Well, through two ways: temperature and precipitation. Now, usually how this is done is, through measuring these two things over a period of time. And as it says, it is driven by averages. So we take the average over years and years and years to handle climate, because remember, weather is what's happening outside right now. Climate is what happened outside for the last 50 years. Okay, so moving along. So we have this chart. I'm sure you are very familiar with this. This is the Köppen classification chart. And there are 5 different larger classifications from A, B, C, and D, and E. And those are the main 5, and they are broken down into 2 sections based on temperature and precipitation. All right, so if you need to, I'm sure for your final, you will need to take a nice good look at this. So please do so. All right, okay, so we have here your major climate groups. So your A is your tropical humid. That is your wet low latitudes. Think the equator. Think places that get a lot of rain. So usually around the equator, there is this band of moisture that just seems to like belt around the earth sometimes. And there is an amazing amount of rainfall that occurs during this. All right, so B is your dry. There is no specific, there's really no specific latitude for this, because many latitudes can have dry climates. And this is where we define this as a place where evaporation exceeds the precipitation. So there is more removal of moisture happening than replacing. So for instance, there are deserts, and deserts occur at many different latitudes, okay? And then we have your mild mid-latitudes. So this is something that we're pretty familiar with. So those of us here in Alabama are very familiar with the mild mid-latitude because we have very mild winters. But we get those warm, hot summers. So that's something like we have here. Additionally, we have the severe mid-latitude, so which is very cold winters, and then usually about averaging summers. And then we have your polar, which is typically high latitude and very cold, very cold. Okay, let's move along. All right, so now we have your second degree. So when you get that first classification, right, when you classify it as A, B, C, D, or E, you will then have to go to the precipitation to get your second letter. So you have your F, which is wet year-round, and this is typically places that are extremely heavy rainfall. Again, typically over 40 inches of rain per year. That's a lot of rain. Also, your monsoonal precipitation. So this is particularly common in the Southeast Asia, in India, Korea, area places like that, where you get a lot of precipitation all at once, and then typically the rest of the year is you don't get as much rain. So then you have your W, which is dry in winter but rains in summer, which is part of the northern United States tends to get this, where you're dry in summer, rain in winter is your S. And then the capital W is your arid desert. Your arid desert. So you might also be asking, why do we have two W's here? Well, we have to ensure that you put them in the right case, uppercase and lowercase. It does make a difference, and it will throw off. Your classification if you put lowercase, because some of these do share. So here's a large W for your arid desert, typically less than 10 inches of rain a year. Okay. Think like the Sahara or the Gobi deserts. Then you have your big S, which is the semi-arid steppe. The semi-arid steppe, greater than 10 inches but less than 15. Then you have your ice cap. Your ice cap, which is where you get into the Arctic and parts of the Antarctic.
Can you close the PowerPoint?
We should do it.
I put a map for you.
Yes, hang on, students. For me?
Yes. It's after
Just for you.
you'll
Just,
see it.
we're gonna reload it.
Yes. And then just keep proceeding.
Okay.
So you-
Ta-da! Then present.
It's a beautiful map.
It's a beautiful, is it like after this?
Should be. It's all the classification.
Oh, okay, I was like, what'd you do?
Thank you, sorry.
Okay. All right. And the last classification is Big T, the tundra. The tundra. You get places like this in northern Canada and Alaska. Okay. And then your third degree, which is your temperature distinctions. All right. So you start off with lowercase h, which is hot desert or steppe with an average annual temperature of 65 degrees. So average annual temperature. So again, remember, weather is what's happening outside right now. Climate is the average of what's happened in the last 50 or so years. And this is how we get these classifications. K is your cold desert or steppe. This is where your average annual temperature is below 65 degrees Fahrenheit. All right. A is your hot summers, the warmest month above 72 degrees Fahrenheit. We are very much used to that. All right. Then we have B, which is warm summers, which is the warmest month is below 72 and 4 more months above 50. And then we have lowercase c, cool summers. Cool summers where the warmest month is below 72 degrees Fahrenheit and 3 months above 50. And very cold winters where the coldest month is below -35 degrees Fahrenheit, which is really cold. All right, here we have a nice map that shows many of the climate classifications around the world. And again, remember that climate classification is driven off of vegetation. So a lot of this is based off of looking at localized vegetation around each one of these continents. So as you can see, this is actually a great breakdown because it has all three classifications. Now remember, I'm sure in your previous labs you talked about scale. So maybe at a larger scale, when you're looking at a smaller area, it might change in those areas. But this is overall a great example of this. And as you can see, typically the part of the United States that we are in is CFA. So let's go back and look at that. So C is mild mid-latitudes, that's mild winters and warmer hot summers. And then lowercase f, so wet year-round, typically over 40 inches of rain per year. And then A is hot summers with the warmest month above 72 degrees. Okay. All right. So this is a climograph. That's what this is. So this is how we measure or we chart how people who work in weather or climate fields, or maybe even you are doing research that's adjacent to this, chart this. So we have the blue bars, right, that measure blue, so obviously precipitation, and the red chart that goes there, which this measures temperature. Next slide here. So here we have one of Nuevo Rocafuerte in Ecuador, and you see the blue bars right here that are showing you the precipitation. But you notice, compared to the last temperature line, so this is a CFA, right? So in January and February, we're low. We tend to peak in July and then come back down over the fall. But as you can see here in Nuevo Rocafuerte, you have almost a straight line. Almost a straight line for temperature. All right. So here we have Riyadh, Saudi Arabia. So you can see that there is very little rainfall. Very little rainfall. Okay. But the temperature is really high, so you get the idea that this is probably a desert-like area. And then you have Elko, Nevada, which has very little rainfall, but a much more pronounced temperature curve throughout the seasons. All right.
I have a question.
Yes.
Any tips you would recommend us try when determining the climates?
Work backwards. Start with the temperature and precipitation first. So actually, let's cycle back let's go to the chart. Right. Every time I teach this, I advise my students to always work backwards. So start with temperature. Look at the temperature first, and then go to the precipitation. Sometimes it will help to at least get an idea of what area you're working in. But when you get into the B's and C's, the C's and D's, the C's and D's can sometimes overlap with one another. You'll see things, and it will be very difficult to try and figure out which is which. So always work backwards, but at least try and get in the same neighborhood. So if you're looking at this chart right here in Riyadh, Saudi Arabia, you're obviously not going to be in a polar region. But you will notice that you'll be like, wow, this has very little rainfall. But then you look and you see what letter that might be under. And then you go and you look at the temperature curve. So the best tip I can give you is work backwards. Yep.
All right. Another tip is remember precipitation is about totals, temperature
Yes.
is about averages.
Yes. As Emily just said, precipitation is about totals and temperatures are generally done by averages. So that is something that is very important to note. As you see here. So average precipitation total, 4.4 inches a year. That's nothing. There are significant rain events here in the south that have given us this in a day. Now those tend to be pretty catastrophic, but they happen. Whereas this is year-round. Year-round. All right. But also the average annual temperature is ridiculous. 77 is on. I hope I answered your question clearly enough. Thank you, Emily, for also clarifying there. All right, so yes, Antarctica, Vostok Station. If you've ever seen The Thing, if you've ever seen John Carpenter's The Thing, or the crappy remake, that happened here in Vostok. This is one where you see that there is almost no precipitation. Almost no precipitation. Something of interest that a lot of parts of the Arctic and Antarctic are actually closer in climate to deserts than they are anything else. But the temperature makes all the difference here because you don't see most arid deserts with a temperature curve like this. Also note that the high temperature on there is -25. So that's pretty bad. Okay. All right. That seems to be the end of this PowerPoint. So, is that the end of the PowerPoint?
Yes.
Okay, that's it. All right. So, take your final and good luck. And any questions? We can leave it open for questions for 2 minutes. Get to go take my seat. Or I can answer questions if you need.
Okay, so for all in-person students, your final exam, well, all final exams are next week. For in-person students, your final exam is during your regular class time. It will be online though. It's all, there's 40 questions. It's pretty much, I think, multiple choice. There's some fill in the blank, but it's 40 questions on labs 1 through 9. And if you're in person, you take it during your normal class time. So if you're Monday 12:30 to 2:30, you take it Monday 12:30 to 2:30. And so take it during your class time. If you, for some reason, cannot take it during your class time, you need to let one of us know. Let your lab instructor know for whatever reason it is. If you're online, if you're an online student, you have that week. So opening Monday, your exam opens, you have until that Friday to take it. Do not forget to take your final exam, super important. So if y'all have any questions at all though, always feel free to reach out to us. We're here to help. Again, we just talked about labs 6 through 9, but labs 1 through 5 are still on the final. So don't forget to review those two, watch the midterm review. We go over all that stuff that's on the final. So watch both these videos. And again, email us if you have any questions at all. But that's it for this final review. Thank y'all for watching and good luck on your exam.